Okay, so for problem number 6, a thick spherical shell, inner radius A, outer radius B, is made of dielectric material with a frozen polarization. So we have P, vector P, R vector is equal to K over R with the unit vector R, where K is a constant and R is the distance from the center. There is no free charge in the problem. Find the electric field in all three regions by two different methods. So the first method that we're going to use is the locate all the bound charge and use the Gauss laws, closed surface E, vector E dotted by the derivative of A is equal to Q enclosed all over epsilon naught to calculate the field it produces. And the second method is use the enclosed charge vector D dot dA is equal to QF enclosed to find the vector D, then find the electric field or vector E using the vector D is equal to epsilon naught vector E plus vector P. So if we analyze the figure, we're tasked to find the electric field in three regions. So first region is the this part. If R is the distance from the center, therefore this part of the region is we're going to find. So the inside of A in this region. So we will assume that R is less than A. If R is less than A, therefore we're probably measuring the volume of the inside sphere. And next region is the region from the outer part of the thick spherical shell. So this outer part, so probably, or we're going to find the electric field at this point where R is greater than B. So probably the surface of the spherical shell. And finally, we combine this the total of this one. So we'll have A is less than R and R is less than B. So if B is greater than R, therefore we will be measuring this part of the sphere, this part between the surface and the volume of this sphere. We also need to discuss some equations and derivations that we will going to use in solving this problem. So we have we'll probably use the bound surface charge, which is this formula, and as well as the bound volume charge, which is rho negative delta del operator dot P, vector P. And finally, we have conditions to consider in finding this symbol. So we'll have this condition. Tau is equal to P vector P dot unit vector N. We'll have a condition that if it's positive vector P dotted N hat is equal to K over B at R is equal to B. And also if it's negative, P vector P dotted by vector n, unit vector n is equal to k over b, k over a at r is equal to a. What else do we need to equations to consider? We also have this equation, which is vector r is equal to k over r hat, the frozen polarization, as well as the Gauss law. So if we remember, the formula for Gauss law is vector E is equal to 1 over 4 pi epsilon naught q enclosed r squared r hat. Okay, so let's try first using the bound surface charge. Again, the formula is this is, if I'm not mistaken, tau p dotted by n hat. If you recall, the p or our frozen equation is k over r hat. Okay, so if we substitute it by this equation, we'll have negative, what is p again? This is k over r hat and dotted by n hat. Okay, or equal to, since you already have unit vector, let's just have negative k over r hat. Okay, next is we use the bound volume charge density, which is rho is equal to negative del operator dot by p vector r multiplied by vector r. So we'll have a del operator, which is 1 over r squared, partial derivative of with respect to r, multiplied by r squared pr. So this is a constant. So let's just substitute the value of p here. Okay, so we'll have 1 over r squared, partial derivative with respect to r, multiplied by r squared k, this is r squared, this is, we use this one, k over r. So we'll just have to cancel this out. No, this one. Cancel this one. Okay. So of this one, so cancel r squared to r squared, and if we get the partial derivative of this one, we will get k over r squared. If I'm not mistaken, we have a negative sign here, so let's not omit the negative sign. Let's put for a is greater than r, or r is less than a, we have to use the Gaussian Gauss law, which according to the given, or the equation, we're finding the electric field using the Gauss law. So we'll use the Gauss law. We'll have E is equal to, since we have the previous equation, we'll just consider it, so we have negative k over r, q enclosed over r. Say this for a, for the tau, so we'll have this one, this tau, yeah, we use this one here. So q enclosed is 0. Why we consider q enclosed 0? Because there's no free charge. So therefore q enclosed is equal to 0. So therefore if we substitute 0 here, negative k over r, 0 over r, we'll have negative k times 0 is 0, then 0 over r squared, let's put it 0 over r squared. Is equal 0 divided by r squared will be equal to 0. Therefore, the electric field is equal to 0. Okay, so let's solve for the volume, the outside part of the sphere, the electric field outside. So for that, we have 4 r is greater than b. So we'll use again the previous equation that we'd use in the letter A, the inside. Conclude that the electric field inside is 0. So let's solve for this one. So we have vector E is equal to negative k over r squared, where negative k comes from the previous solving here, this part, the row, and so we substitute it here, and as well as the q enclosed. And therefore, we'll have, according to the divergence theorem, if you recall the divergence theorem, we'll have, so recall the enclosed surface of P, vector P dotted by dA is equal to integral of the volume del operator dotted by vector P d tau is equal to this one. So we'll have, so our Q enclosed is also equal to 0. It's very obvious that it will be 0 since there's no free charge according to the problem. So therefore, if we substitute Q enclosed with 0, we'll have E is equal to negative k over r squared multiplied by 0. We will get 0. So there our electric field outside the spherical shell is equal to 0. Finally, for solving this part of the figure, the inside, the part in between the volume and the surface charge, we'll have to deal with this condition for A is less than or is less than B. So we'll have to combine everything, and we have to use this equation Q enclosed. We have to first find the Q enclosed first before we go to the Gaussian Gauss laws. Since this is a combination, we cannot just assume that it is 0. So we can if we combine equations, so we have the enclosed surface of tau A d A plus integral of V rho P dt. So we have to transpose. So the previous calculation again, the value of this one is negative k over r, or let us assume that A is equal r is equal to A, since we are dealing with A. So and then the dA is 4 pi, instead of r we'll just put A squared. This is the area of circle, as well as plus the integral, the difference between A approaching B. So the value of this symbol is, you have negative k over r squared multiplied by dt of 4 pi r squared dr. So here in this part, we retain r. Anyway, we'll just substitute it from this potential difference. We'll have to cancel a here, a there. We're left with negative 4 pi k a and then plus we have to cancel r, these two r's. What else do we need to put here? So the derivative of r is r, so we're left with this equation, negative 4 pi k r. Okay, and then we now put this one, so we'll have negative 4 pi ka minus this one, positive minus negative is negative 4 pi k a k, we need to substitute this one, so have r minus a. So the enclosed charge enclosed, if we simplify this one, distribute this one, we're left with negative 4 pi k r. So if we want to elaborate this one, let's just write it so that we can see. Negative 4 k r, distribution 4 pi k r. Another distribution, negative times negative, positive, positive 4 pi k a. So notice that this will cancel since this is negative, this is positive. Yeah, so our charge enclosed is equal to the negative 4 pi k r. So this is our Q enclosed. We're not still finished. We'll just solve for the electric field using the Gauss laws. So we'll use this equation. E, the electric field is equal to 1 over 4 pi epsilon naught multiplied by Q enclosed. The charge enclosed we calculated earlier, r squared. So if we substitute the Q enclosed we get earlier, we have 1 over 4 pi epsilon naught, and then Q enclosed is negative 4 pi kr r squared. So we cancel r. What else can we cancel? We can cancel also 4 pi. What else? So yeah, nothing. We can cancel nothing. Let's put our hat here so that we can indicate the electric field is a vector. So we're left with negative k over epsilon naught r and then r hat for our electric field. So we get the 3 electric field in all bound charge. This is for just the first method. For the second method, we will use the equation. In the second method, we will use the enclosed surface of d, vector d dot dA is equal to q f enclosed to find our electric field. But before that, let us also define other equations. Let us put the equations we're going to use so that we will not get confused, as well as this one. This equation is given to the problem, as well as this equation. D is equal to epsilon naught electric field plus the vector P. And also we will not forget the equation to solve earlier on the first method. So we'll just put it here. E is equal to vector E is equal to negative k over epsilon naught r hat. Okay, so let us first solve for the D outside. the outside, the D, vector D outside here. So we'll use the equation D dot dA, vector D dot dA is equal to Q enclosed. So dA again, solving for the circle or sphere, therefore our dA is equal to the vector D dotted by or multiplied by 4 pi r squared, and is equal to Q enclosed. So after that, we want to be left with the D out only. So we divide both sides by 4 pi r squared. 4 pi r squared cancel. So we're left with D out is equal to Q enclosed 4 pi r squared. Like the reasoning out on the first method, there's no free charge outside. Therefore, the charge here will be equal to 0. So the charge is equal to 0. If we transpose the charge as a 0, therefore, we'll have 0 over 4 pi r squared. So that's D out. This is the D out. Okay, so if we do this 2 to the D in, it will be the same. So therefore, our Dn, we can therefore conclude that Dn is also equal to 0. So Dn and D out is, if Dn and D out is 0, therefore D is equal to 0 everywhere. So next equation to be used is D, vector D is equal to epsilon naught vector E plus vector P. So recall that our electric field that we're going to use is the electric field that we solved on the first method. Okay, so we will just substitute everything that we know, but first let us manipulate E, the electric field. We manipulate this equation that we use. E is equal, we solve E is equal to negative K over epsilon naught R hat. So it can also be equal to negative 1 over epsilon naught and multiplied by K or R hat. If you recall again the previous formula, if you're familiar with this one, this is equal to P, vector P over multiplied by vector R, right? So if that is so, we can conclude that the electric field's value is equal to P, vector P multiplied by R, vector R is equal all over epsilon naught. So this is now our value for the electric field. Now let's substitute everything by using this equation. So we have D is equal to epsilon naught. Our electric field is this one. This is our new electric field. So we multiplied this by negative, I forgot to put the negative here. We already have negative here. So we put negative here, and PR, or it's just P. I don't know if that's what you like. If you like to put R or not, it's just okay. Epsilon naught plus P. Let's check. Epsilon naught E. This is our E. Substituting this one, and finally plus P. Okay. Now we can cancel epsilon naught. Canceling it, So we're left with negative p and positive p. If we try to manipulate this one, it will equal to 0. Therefore, vector D is equal to 0. So if we try to summarize everything that we get, we'll have, since we considered that our electric field is we adopt this electric field. Therefore, for the summary, we'll have A greater than or greater than B has electric field of be equal to negative K over epsilon not R. If we want this to become vector, we'll just put a arrowhead and a unit vector R. So for R is less than A and R is greater than B, our electric field here is equal to 0. And if we try to take a look at this one to the first methods, it is correct. If we compare the first method to the second method, it is correct. So at this part and the yellow highlighter and the green highlighter, this is 0. And for between the green and the yellow, we'll have negative K over epsilon naught R.